Good morning, everyone. Welcome to Nano Open Webinar. We have Peter Steeneken from Delft University of Technology today. Professor Steeneken is one of our TeamNANO researchers. He will talk about sensing sound, motion, and magnetism with 2D materials. Before Professor Steeneken starts his presentation, I would like to give you a brief introduction about him. Peter Steeneken is full professor and department head at the Precision and Microsystems Engineering Department, leading the group Dynamics of Micro and Nanosystems. His research and teaching focuses at the dynamics and physics of mechanical systems at the micro and nanoscale, particularly focusing at sensing applications. He aims at enhancing our understanding of physical principles and materials properties, realizing improved measurements method and models for novel and improved devices and applications. Professor Steeneken has a PhD in physics and more than 14 years of experience in industrial research labs at Philips and NXP. Dear Professor Steeneken, welcome to Nano Open again. The stage is yours.
Okay, thank you very much for this nice introduction. Let me share my screen. I hope you can see it this way.
Yes.
Okay, let me move this a little bit aside. Okay, good morning, everyone. Nice to be here, and thank you very much for the invitation to give a presentation here at the Nano Open Webinar. Today, I would like to tell you about the research we have been doing on 2D materials, first focusing on how we can actually understand the properties of these 2D materials by using nanomechanical motion, nanomechanical resonance. And then in the second part of the talk, I will focus more on how we can use these 2D materials to create sensors for things that we cannot sense at the moment, or improve the current sensors. So this work was done in a collaboration with many other groups here in Delft, but also abroad, like the group of Coronado in Spain. Before I go into the details of the presentation, I would like to tell a little bit about the TeamNANO project that we recently started. So last month, we had a very nicely organized kickoff meeting at Sunum, Sabancı University, which was organized, which was really a very nice event where we met all the people and all the stakeholders related to this TeamNANO project, which is funded by the European Union and by TÜBİTAK, and which involves TU Delft, Sunum, of course, and University of Southampton. And the goal is capacity development and synergy in the micro and nano fabrication and flexible electronics. And also, so to develop those technologies, to develop centers of excellence in Europe and the European research area, and also to actually bring this to the market eventually. So on the right side, you see here the different activities. So Delft will focus on micro nano engineering, sensors and 2D materials, and MEMS and NEMS. And the University of Southampton is bringing in the printed electronics and e-textiles, nano-electronic devices, and photonic integrated systems. And at Sunum, they will work together with us on bringing this technologies also to strengthen the nanofabrication expertise and capabilities at Sunum. So together we can then realize new devices, especially in the micro and nano realm, and also flexible and wearable electronics. So I'm looking forward to this project. It will take 6 years. And yeah, I think we had a very nice start already, but you will for sure hear more about this later. For now, let me go into these 2D materials. Why are they so interesting? And I want to start and discuss three types of 2D materials. First of all, I want to explain how we can measure magnetic properties of 2D materials by using their mechanical resonances. Then I'll discuss the thermal properties. They are also unique. And finally, I would like to discuss how we can sense sound and also particular types of sounds that have never been heard before by using 2D materials. So why is magnetism in 2D materials so interesting? This is really an emerging field. And the reason is that if you have a magnetic materials, it consists of magnetic spins. And in 3 dimensions, those spins are interacting. However, if you thin down the material, you reach the 2-dimensional scale and the interaction between the spins is changing. So you can get new types and new phases of magnetism that cannot exist in 3 dimensions. And here on the slide, I've shown 3 types of phases that can occur. You can have the spins all aligned in one direction. So this is called the spin dimensionality of 1. You can have the spins oriented in the planes, so they can orient themselves in 2 dimensions, and you have the orientation in 3 dimensions. And what is shown below is the magnetization, so that's this M. And you see that only this first case can show a remnant magnetization, which means that the spins stay fixed in this orientation, whereas in the other case you cannot. However, in the susceptibility, that's how sensitive the material is to an external magnetic field, you do see also different behaviors. So the question is, when do we reach these 2-dimensional states? How can we understand the different types of ordering? What can we do if we put different 2D materials on top of each other by creating heterostructures? Then you can create new properties. And then if you have a very thin material, you can also more easily strain it. And what is the effect of the strain? And the strain can go in 1 dimension, but also in 2 dimensions. So you can also create anisotropic strains. So this figure explains a little bit more the different types of ferromagnetic and antiferromagnetic ordering that can occur. So if you have 2 layers of 2D materials, which are each 1 atom thick, and you stack them on top of each other, you can have a situation where all the spins are pointing in the same direction. So this is the ferromagnetic ordering case. However, you can also have cases where the spins are pointing anti-parallel. And there's 3 types of way of ordering. And actually 2D materials have been found that exhibit all those 3 different types of antiferromagnetism. And the type of antiferromagnetism that occurs depends both on the magnetic coupling between the spins in 1 layer, but it can also depend on the coupling between the spins in different layers. And those spins coupling strengths, they're indicated by the letter J, and they can depend on the type of material, but also on the distance between the layers, for example. So we would like to investigate this, but this is not easy because there's very few probes to actually detect spins in such a thin layer. And especially when the material becomes antiferromagnetism, then the magnetic fields of these spins are canceling each other, and it's very hard to detect. And of course, the volumes of these samples are very small because they are only 1 atom or few atoms thick. So we set out to see if we could use nanomechanical resonance as a tool to probe these new phases of magnetism. And how do we do it? So you cannot easily contact something. So we were looking for contactless methods to actually study the nanomechanical resonances. And for that, we use this technique where we use a blue laser, which is heating the membrane a little bit, whereas the laser power is varying in time. And as a consequence, the membrane heats up and cools down in time and expands and contracts as a consequence. And as a result of that, it starts moving. And if you do it at the right frequency, you can also bring it into mechanical resonance. But then the second question is, okay, how can we actually measure and know if it's really resonating? For that, we use a second laser, a red laser. And there's a kind of the substrate below the membrane, which acts as a mirror. And if this red laser reflects from that mirror, it creates a standing wave pattern. So it creates a standing wave pattern with nodes and antinodes. And when the membrane is moving through this standing wave pattern, it absorbs less or more power and attenuates the reflected light by its movement. So if it's in a region where there's a high red laser intensity, then it absorbs more and you get a low intensity on your detector. Whereas if it's in the middle, it absorbs less energy and you get a higher intensity on your detector. So we use a setup to have both these blue and these red lasers hitting our membrane, which has a diameter of about 5 micrometers and is a thickness of a few nanometers. And we separate them with this special filter. And then we use a network analyzer to generate the modulation of the blue laser and to detect with a photodiode the intensity variations of the red laser. And then when we change the frequency of this blue laser, we see that at a certain frequency, in this case of 26 megahertz, we get a resonance peak. So we know that the membrane is in resonance at this particular frequency. And this whole setup is in a cryostat, which can be cooled down to 4 Kelvin in high vacuum. So we can track actually this resonance frequency as a function of temperature. So that's what we did here. And what we did, what we see when we cool down, we see that this resonance peak is increasing in frequency, but we also see something peculiar here. So the slope is steeper around about 114 Kelvin. And we try to understand that. And to understand it, we should realize that this membrane is like a string, like a guitar string, which becomes tensioned when there is stress on it. And the stress is caused by the temperature change. So the substrate, so the size of the membrane by which it's clamped, is expanding less or contracting less than the membrane itself. So that causes that the contraction of the membrane, I think I have a picture here. So when you cool it down, the membrane contracts and it becomes tensioned and the resonance frequency is increasing. So strain is generated, so you get this tension. So by monitoring this resonance frequency, we can calculate how much strain and stress there is in the membrane. And by looking at the temperature dependence of this resonance frequency, we can also get the thermal expansion coefficient. And that can be calculated by this equation. So it's basically minus the temperature, the resonance frequency squared, the derivative of the resonance frequency squared towards temperature. So if you increase again, of course, it expands again and the frequency goes down. One special thing I would like to highlight is that these resonance frequencies are very good measures of the strain and of the lattice parameter of the material. So we can measure this resonance frequency to a very high degree of accuracy. So you see that the resonance frequency in this case is 27 megahertz, but the variation in it is very small. It's only about 54 hertz. So that means that we have a accuracy of 10 to the minus 8 in the stress and the strain that we measure, which is much better than other techniques like X-ray diffraction. So here on the right side, for comparison, I've shown an X-ray diffraction measurement of the same material, and our measurements are a factor 1,000 times better, which actually provides with an accuracy of the lattice parameter of 6 attometers. So we can really see very small changes in the distance between the atoms. I didn't mention that yet, but we have chosen this material because this is one of those antiferromagnetic 2D materials. And we also went to a synchrotron in Germany, Hamburg, in April to also measure the lattice parameter by in a synchrotron. So you see here behind us, you see the X-ray diffraction, X-ray diffractometer, and there was an X-ray source from the synchrotron by which we could also measure this lattice parameter. And what we saw there is that actually this lattice parameter's X-ray diffraction is even harder to do on these membranes because the membrane, if it's a little bit bent, these diffraction peaks are broadened, and that's why you see here this kind of circular spot. So our resonance frequency measurements are a better way to study lattice parameter than these synchrotrons, was our conclusion. Okay, so we can measure this thermal expansion coefficient alpha, but how is that related to the magnetism in the material? To understand that, one can look at this material as a kind of a balloon, which is filled with phonons, electrons, and magnons. So these are excitations in the material, and they create a kind of a pressure on the balloon. So then if you start changing temperature, for example, if you increase the temperature, you create more phonons, electrons, and magnons, and we're especially interested in these magnons because they are the magnetic excitations in the material. And those properties are related to this specific heat by this equation, which tells us that actually the number of magnons that you create by increasing the temperature is given by this factor, which is the specific heat. And we can relate the two by this equation. If we also take into account this factor, which basically states what is the effect of this energy on the volume. So the volume change is a consequence of the generation of extra magnetic excitations in the material. And well, you have, of course, magnetic excitations, but you also have lattice excitations, so phonons, so these are lattice vibrations, and you have electronic excitations. So by monitoring this thermal expansion coefficient, we can study the phonons, the electrons, and the magnons. So we can really study the properties of this material. And then this vector, this prefactor, consists of the Gruneisen parameter and the bulk modulus of the material. So what happens now if we do this calculation? So we determine this thermal expansion coefficient, and this gives us this purple line here, and it shows a huge peak close to the temperature of 114 Kelvin, at which this material, our iron phosphor trisulfide, becomes antiferromagnetic. So above this temperature, the spins are still randomly aligned, but below it, they all become nicely antiparallel organized. And this peak basically tells us that these magnetic excitations are strongly changing actually at this temperature. So if you start heating the material, here it's still magnetic, but around this temperature, you have to add a lot of energy to still break this magnetic order that is there in the structure. It's a little bit like melting an ice cube. So around 0 degrees Celsius, you have to put a lot of energy to melt the ice cube. And this peak here is basically a peak in a specific heat, which means you have to put a lot of energy to, in this case, melt the magnetic spins. So you're melting the spin lattice. So this shows that with these magnetic resonance measurements, we can actually study those magnetic properties of this material. We also did it in other 2D materials. For example, this material tantalum disulfide, it has a charge density wave, so it has charges that are ordered, and around this temperature of about 70 Kelvin, we have to melt them. So you see such a peak. Then we also started looking if we could look at anisotropic materials. So here we studied cobalt phosphor trisulfide, which is also such an antiferromagnet, but we created rectangular membranes. So instead of the circular ones that we had before, these are rectangular, and we made many of them, but we oriented them in a different directions. So this is a single crystal. So that means that some of those rectangles were aligned with one crystal axis and the other ones or aligned with another crystal axis. And the interesting thing about these rectangles is that the resonance frequency is mostly determined by the shortest direction. So what you see if you then start heating and cooling the material is that the resonance frequency really is different for the rectangles that are oriented horizontally from those that are oriented vertically. And we started looking at this temperature dependence, and this can be understood by looking more at the crystal structure of the material. So here you can see that these metal ions, so these cobalt atoms, they are oriented in hexagons above the Neo temperature. But if you cool it down, you get these antiferromagnetic orders where the magnetic spins are up on this red line and they're down along this blue line. And these magnetic ions, they repel each other. So the membrane starts to expand in one direction and contract in the other direction. So the magnetic ordering causes a variation in the strain in these membranes. And you can imagine that if you have a membrane that is vertically here, the membrane tries to contract, and that leads to a larger frequency increase, so like a guitar string, than if the membrane expands, like you see here in this blue line. Well, it's known that this kind of expansion due to this magnetic order is given by a magnetoelastic parameter. So we can relate this strain and stress that occurred to the magnetization of the material. And these magnetoelastic parameters are then depending on the direction in the crystal. And if you do some math, you can actually relate the resonance frequencies to this magnetization, and we can extract this magnetization curve. So that's what we did. So we take the difference of the resonance frequency square along the two directions, so for the 0 degree and the 90 degree, and then we get a curve that is related to the magnetization squared. And that's interesting because getting the magnetization close to this Neo temperature is very interesting and hard to do with other methods. So we use this technique to study different materials, not only this cobalt phosphor trisulfide, but also the iron and the nickel compound. And by monitoring the temperature dependence of this magnetization that we extract close to the Neo temperature, we can test what kind of magnetic order takes place. So these dashed lines here are different models for the magnetic order. And we can now, for each of these material, see how this magnetic order, what kind of magnetic order there is in the material, but also how it depends on the thickness of the membrane. And we can also look at the Neo temperature, so the temperature at which a phase transition occurs. So we discussed with theorists, and we can also compare our results to some of their numbers. So the bottom number is the theoretical number, and this is what we found from our experiments. So there's still some discrepancy, so better theories are still needed to fully understand these measurements. So we can do more. We can also add strain. So one way to add strain is to put an electrostatic force. So we generate a voltage between the suspended membrane and the substrate, and then we can pull it down and look what happens to this Neo temperature. So we can shift actually this Neo temperature by strain. And for the antiferromagnetics, we saw that this Neo temperature is going down, whereas for a ferromagnetic 2D material, like this chromium germanium telluride, you see it going up. So this nanomechanical resonance presents a way to study these 2D materials and also, yeah, how they behave under strain. A final topic that we tried is to make stacks of 2D materials. So we put two different 2D materials on top of each other, and then when we cool this structure down and we look at the resonance frequency, we can actually detect the phase transition in the first material, that's the iron phosphor trisulfide, and in the second material, which is the CGT, the chromium germanium telluride. There's many unexplored effects still. So for example, also the Q factor, which is the amount of damping that occurs in the material, is very temperature dependent, and these things are still not understood, so still a topic of investigation. Okay, so these were the magnetic properties. Now I would like to turn to the thermal properties of these 2D materials. So like I said, we actuate them with a modulated blue laser, and that heats the membranes, but the heat also has to leave the membrane. And what we can use is we can use the thermal expansion coefficient as a kind of thermometer. So how does it work? If you have this material, you heat it by an amount delta T, then by the thermal expansion coefficient, it moves a distance x, which is a linear relation. So this means that we can use this deflection, at least if we're not on the resonance, so if we're far below the resonance frequency, we can use it, this deflection that we measure, as a measure of the temperature change. Of course, we need to find this coefficient in between them, but if we're only interested in the time scales at which these temperature changes occur, this relation is enough. So how does it work? We increase the laser power, then it takes some time for the temperature to increase, and the time is characterized by a certain typical thermal time constant, tau, after which we measure the motion increase, the x. So you can model it by an RC system where this tau is the RC time. So the force, or actually this temperature increase occurs a little bit later compared to the increase of the laser power. And this thermal time constant tau we can measure from our frequency response measurements. And if we look at the real and imaginary part of our response, the time tau is characterized by a peak in the imaginary part of our experiments, which is shown here. So we can convert the frequency of this peak to a time, and those times are in the nanosecond range. And we made a model to actually use that thermal time constant in combination with the resonance frequency and some AFM measurements to characterize the thermal properties of the membrane. So we characterized the specific heat and the thermal conductivity, and we compared our measurements to experimental data from other works. And we did that for membranes of different thicknesses and different material properties. So here are the different materials. So the circles are our data, and the triangles are literature values. And you see that for each of these materials, our circular points are quite well matching the literature data that was there up to then. So this shows that the thermomechanical resonance can also be used as a tool to characterize thermal properties of 2D materials. However, when we tried this for graphene, we found that this model that we had didn't work well. The time constants we found, so the time it took to heat up graphene, was 25 times larger than what we expected from our model. So we started investigating this more, and we had the hypothesis that this was caused by a thermal resistance that exists at the boundary of the graphene. So the graphene is not perfectly flat when you put it on such a membrane, but by the van der Waals forces, it adheres here to the substrate, which bends it a little bit at the edge. And as a consequence, heat that travels from the center of the graphene membrane to the edges finds here a thermal impedance, because part of these acoustic waves reflect from the edge instead of being transmitted to the supported part of the graphene. We also made a model which could explain this increased resistance. And this is probably why the thermal transport of a graphene membrane is much slower than you would expect, but purely based on its material properties. Then we thought, well, if this is really so important, can we also tune the speed by which heat is transported over a graphene membrane by increasing the tension in the membrane? So thermal energy is transported by sound waves. So if we can increase the speed of sounds in the material by tensioning it, we might increase the rate at which heat leaves the membrane. So we applied the gate voltage on the membrane, so we pulled it down. And we saw here also that the resonance frequency was increasing when we were doing that. So you see it, especially on the blue and the green, you see that the resonance frequency started increasing. And at the same time, we measured this thermal time constant, and we saw also that the thermal time constant was decreasing when we did this. So this looked like this hypothesis worked. So we could increase the speed of heat transport by tensioning the membrane of the graphene. However, when we started modeling that in more detail, we saw that indeed in the resonance frequency and the speed of sound do depend on the tension, so on how much tension we put. But actually, if you look more into this, at higher frequencies, the speed of the phonons in graphene, so the speed of sound, depends mostly on the bending rigidity kappa and not on the tension N anymore. And actually, most of the heat is transported by lattice vibrations, so phonons, which are in this high frequency regime. So that means that, yeah, that actually this model that we had could not explain what we saw in the thermal time constant. So then our final conclusion was that probably it's not so much the speed of sound in the graphene itself, but it's more the effect at the boundaries that determines what happens with the heat transport in graphene. So when you tension graphene, the angle that happens at the edges is changing, and that is changing this thermal resistance at the edges. Besides 2D materials, we are also trying to work with these string resonators, which are made out of silicon nitride. And I just want to show you one slide because I think it's quite a nice result. This is with my colleague Richard Norton. And here the goal is to limit the damping as much as possible to make extremely sensitive sensors. So it's a slightly different topic. But what we did is we created these silicon nitride resonators. So these are strings which are 3 centimeters long. And we create a kind of resonance in the middle. And what you see here are special structures which act as mirrors for sound. And by creating these mirrors in the right way, we can confine the acoustic resonances in the central region of the beam, and as a consequence that they're confined, they don't dissipate any energy. And this eventually resulted in resonators that have a very high quality factor. So the quality factor of a resonator is a measure of how many times it basically keeps vibrating after you excite it. So in this case, a record value of more than 6 billion for the Q factor was obtained. And this design was not so easy to come up with. And actually some machine learning techniques were used to actually create this design. So on the bottom left, you see this machine learning process where multiple iterations for various designs were used to eventually reach the final design that was used to create this record value of the Q. So on the right, you see the Q factor that was obtained for the different designs. And eventually, the best design was found after many iterations. This optimization of resonators is also important for other types of resonators. And you can, of course, do this with machine learning, but there's other optimization techniques like particle swarm optimization. And the nice thing about that is that you can optimize multiple parameters at the same time. So here we create a kind of model system, also again a silicon nitride string, where we try to optimize the support of it. So for a sensor, you would like to have it response fast. You would like it to be able to detect very small signals, and you would like to operate it at very low power. So what we did is we created a model, a finite element model, that captured all these different parameters based on the geometry of the resonator. And then it didn't only include the linear dynamics, the linear properties, but also the nonlinear dynamics. And by optimizing it, using this particle swarm optimization, we let the computer do many iterations and look at the trade-off between these different parameters. And such a trade-off is called also a Pareto front. So you create a kind of optimum design where your objectives are along different axes, so that you can then, after making that front, you can kind of select design that has the best trade-off for your specific application. Okay. Now, as a last part of the talk, I would like to look a little bit more on how to detect sound with 2D materials. So this is a bit more application-oriented work. And we did many of this as a part of the Graphene Flagship project, in which I collaborated with my colleague Stan Vollebrecht and some PhD students. And here you see some of the graphene microphones that we made in this Graphene Flagship project. On the top right, you see the compliance. So that's basically how sensitive these microphones are. And the microphones we made were more sensitive than most of the literature values, both MEMS devices, which are in blue, but also other graphene microphones that were published. And we were able to, oh, I'm sorry, I think I lost now maybe the sharing. Let me share again. Okay.
Yes.
So I don't know, can you hear it or not? Maybe not. Let me try it again. I just stopped share for a while, because I think I have to share including the sound. Yes, I should share like this. So this was I think now you can hear it. So this was a recording by this graphene microphones. So we can actually record sound. We are now working on including electronic readout. We had the first evidence that we can do electronic readout, but we don't have a good sound quality yet. So the sound that you heard was obtained by optical readout. But besides microphones, we also detect biological sounds. And I have a small quiz for you, where I will play 4 different soundtracks, each belonging to one of these biological sources. And if you like, in the chat, you can indicate which you think is which sound. So, for example, if you think that sound A is the caterpillar, you type A1, etc. But you don't have to do it, but maybe try to think which one you think it is. Oops, I should click here correctly. That is the first soundtrack. Here I have the second soundtrack. So only 2 of them were actually recorded by our devices. The other 2 are taken from literature. Oops, should click correctly. Okay, it's pretty hard, I think, but maybe some of you had it correct. Let me give the answers to the questions. So the first sound, this sound what you hear, that's the sound of a plant. And I'll explain later how we recorded this. The second sound, this is the sound of a caterpillar. It came from this Nature Communications paper, so it's not recorded by us. This sound, what you hear here, is the sound of a bacterium. I will explain later how we recorded this. And the last is the sound of a catfish. So this one was not recorded by us, but was taken from this data site database below. So let me first explain the sound of a bacterium. How can we detect it? So what we did is we created this array of graphene drums, and we flushed bacteria over it, and we had a sticky substance, aptes, which resulted in the bacteria sticking on the graphene drum. So here on the bottom right, I don't know if you can see my mouse, here on the bottom right, you see a bacterium fixed to this graphene drum. And what we do then is we use a laser to measure the motion of these membranes. And then the following happens. And the intensity variation of this laser can be converted into sound. So you see here the bacterium stuck to the membrane, but it's swimming. So it moves the membrane. Then we detect its motion and convert it to sound. And then we add antibiotics. And the antibiotics kill the bacterium and the sound stops. So now we know that this antibiotic works on this type of bacterium. But of course, this is a very important question. So doctors want to know as soon as possible when a patient has an infection, what antibiotic to administer. So this can be quite useful. So we did this for different types of antibiotics. You see it here on the slide. Some of them work, like these top two, but for example, this kanamycin does not work, so the motion persists. You see that the spectrum is a kind of a noise signal. It looks a little bit like 1 over F noise. But this is the motion generated by these E. coli bacteria. Since this is a much faster way to detect the effectiveness of antibiotics, we also started a company with these co-workers. It's called SoundCell. And of course, this company has the aim to actually bring this time for antibiotic susceptibility testing down to 1 hour, whereas nowadays it can take 1 or 2 or sometimes even 7 days until doctors know what is the right antibiotic to administer. So making patients better sooner is one of the goals of the company. But another one is also that doctors now prescribe many different antibiotics just because they don't know which one is the right one. And as a consequence, the bacteria become resistant against antibiotics. So the effectiveness of our antibiotics is reducing. And this problem is becoming increasingly damaging. So by 2050, it's expected that 5 million people per year will die because of this antibiotic resistance. And a huge loss, financial losses are also occurring. So the first machines from the company are now being tested in hospitals. So hopefully this will speed up antibiotic testing schemes. Then as a last topic for today, I would like to mention how we measure the sound of plants. This was done with my colleague Gerard Verbiest and some postdocs and people from Wageningen University, Elias Keizer. So what we did, we connected these ultrasound microphones to the stem of plants. And when plants are dry, air bubbles are formed. So basically the water is evaporating from the leaves, and this creates a high tensile stress on the water column. And as a consequence, bubbles are formed. And these bubbles formation is quite violent and causes the generation of a sound pulse. So what we did is so you see all these sound pulse. We just heard them also in the sound recording. But if you look at one of these sound pulses, you see it has this kind of shape. So it has a kind of frequency, but it also has a certain envelope. And we started analyzing the frequency of these pulses, but also the envelope, the time it decays. And we plotted this in graphs. So basically here you see different types of pulses on the top right. So the resonance frequency is one axis and the settling time is on the other axis. And we made a model which is a little bit similar to the model for an organ pipe. So there's two types of frequencies. There's the standing wave, which is like in an organ pipe, depends strongly on the length of the vessel. So the resonance frequency here, if it's high, you are dealing with the short vessel, and if it's low, you're dealing with the longer vessel. But then also the radius of the vessel has an influence on the shape of this decay. So for large diameter vessels, we see a long settling time, whereas for short diameter vessels, we see we're dealing with a longer short radius. Once we're dealing with a short decay time. So we plotted that in a graph. So the black points are calculated by our model, and the red ones are actually measured by these kind of SEM images. So, but for these, of course, you have to cut the plant to do this kind of analysis, whereas these measurements with ultrasound we can do without actually damaging the plant. So for farmers and greenhouse agriculture, this is really useful. And so, we can also distinguish different types of plants. Here you see some examples. Each of them has a characteristic signal. And my colleague Gerard, with some students, started also a company called Plants Technologies to actually mount these ultrasound detectors in greenhouses to monitor the growth of plants, but also maybe it can be used to detect diseases in an early phase. Finally, yeah, I don't have enough time to present this, but we're also doing quite some work on levitation, magnetic levitation by using diamagnetic materials like graphite that levitate above permanent magnets. We're trying to create actuators and sensors. So here we create a mass sensors that could measure water droplet mass. And here we have an actuator with electrostatic force where we can create these rotors. And we're also working on ultrasound. So here you see ultrasound transducers. So arrays of 2x64 ultrasound transducers. And you see here that we can control these two beads by programming these actuators to move them. And we're also creating optical systems to monitor the pressure fields in these ultrasound actuators. So we will soon publish also something about this work. We're also working on combining MEMS with 2D materials. So this is a MEMS actuator where we can actually stretch a 2D material that is put here between these anchors, and we can tune the resonance frequency of this graphene membrane by pulling it, or this 2D material by pulling it, and also studying the slip, so yeah, how to fix it well. Okay, that brings me to my conclusions. I hope to have given you a kind of overview of what kind of things we can do with nanomechanical resonance to study physics, magnetism, and thermal properties, but to sense heat transport and to detect sound, not only sound that we hear ourselves, but also sound of bacteria and plants. There's many challenges, both in the understanding and in creating better sensors and devices, and also in terms of fabrication, how to bring these devices to the market. So thank you very much for your attention. And if there's questions, I'm happy to answer them. And I should not forget, of course, this was not done by me alone. We have a big group of people that contributed to this. So also thanks a lot to them.
Thank you. Thank you for your presentation. Now, Peter, as Peter mentioned, session is open for questions. If you can speak up or raise your hand, or if you like, write in chat box.
Great. Yeah.
No questions?
I have a question, just small.
Yılmaz Hocam,
And
please.
yeah, and is it possible to use your device as an electromagnetic detector?
Oh,
Because
yes, that's an interesting question. So I think there's multiple ways to do it. Yes, so for sure. For example, for detecting magnetic fields, one way that is possible, and I'm not sure if people did it already actually, to see if it can be used as a kind of Lorentz force actuator. So if we would run an alternating current through the 2D material, for example, and there's an external magnetic field, this will generate a Lorentz force on the 2D material, and the amplitude then of the resonance will depend on the magnetic field. And another thing, of course, that can be done is if we would have a ferromagnetic material, then this material itself will be force will be generated on the material by the magnetic field, and this will deflect it. Then the electromagnetic, there's different types of electromagnetic fields, of course. So also electric fields might be maybe sensed, but I have to think a little bit. It depends really on the frequency. The light itself is, of course, an electromagnetic field, so we are already detecting the effect of light. That's actually what we use to actuate our membranes. So if the intensity of the light is changing, we can already detect it. Another idea that is actually I've shown this this string resonators of Richard Norton. He is also working on membranes, and those membranes are intended to become light sails. So they're intended to measure the radiation pressure of a laser, or even to be propelled by laser radiation pressure. And one idea, which is pretty hard to realize, is to create small spaceships that are propelled by light. So you would need this very light sail that is reflecting almost all the light. And then if you shoot a powerful laser on it, you can accelerate it to a very high speed and send it to space.
okay, if there is no question, I have a short question about the electronic excitation when you irradiate your membrane, and there's some resonance. During this resonance vibration, or what we call, and did you get any voltage differences between the two electrodes, which is the membrane is connected? I'm just interested in the electronic excitation.
Yes, so we didn't study that part, but that is for sure possible. So we work mostly with optical actuation and optical detection, but it is possible to do it completely electronically. So the most used method and the most sensitive method for detecting and actuating the motion is to use the electrostatic force to actuate them. So that's what we are doing already as well. But then to make use of semiconducting 2D materials, but well, graphene can also be used to a certain extent, where you basically look. So if the voltage between the membrane and the counter electrode is constant and the membrane moves, the capacitance is changing. And as a consequence, the amount of charge on the suspended semiconductor material is changing. And that creates a varying doping. And like in a transistor, this will vary the resistance of the 2D material. And you can then use the resistance or the transconductance of the membrane as a measure of its displacement.
Okay, thank you very much.
And yeah, that is actually, especially if you want to make these sensors very small, then it is nice to do this completely electronically, because yeah, by having it completely electronic, your system becomes smaller and lower power usually.
Thanks.
We have two questions in chat box.
Okay. I can have a look.
Yes. Not two questions, but wants to ask questions. Haber Aziz'de. But first question is from Çağatay İleten.
Okay. Yes, I see it. What do you think about the potential of 2D TMDC materials for sound detection? Yes, I think, like I said, graphene is not the only material, and some of those. So graphene has the advantage of having a high conductivity, but especially for certain readout mechanisms, other 2D materials could be more interesting. Like, for example, molybdenum disulfide. It is a semiconductor. And if you want to do this electronic readout, I think it is very promising. So then you could the sound would actuate the membrane, and you would measure changes in the conductivity of this material as a function of its deflection to detect the sound. I think these techniques could be used. Another material that's interesting is platinum diselenide, which has a very high piezoresistive coefficient. So in that case, you don't even need that gate voltage. You would just measure the resistance. And some of our collaborators in the graphene flagship from the University of Aachen are actually working on that material to create pressure sensors, for example. But maybe for sound detection, that could also be a possibility. Yeah. So yeah, thanks for the question. That's an interesting idea.
I also have a question, please.
Okay, yes.
Thank you, Peter, for the very nice presentation. So my question is regarding the very high quality device that you have fabricated, I believe, which was 3 centimeter long, right?
Yes.
So was it about the location of those blade types parts that you ended up with this very high quality device?
Yes, exactly. So
My,
I can maybe show it still on the slides. Let me go back. So there was this device.
yeah,
So you mean these ones, right? These.
yeah, because my feeling is that whenever you're adding those blade type structures there, because of the more interaction between them and the air, they may end up with the increase of the damping rather than decreasing it. So it's very interesting to just what they're doing there.
Yeah. No, that's a very good question. But these devices, to reach these very high Qs, we have to operate them in high vacuum. So one of the challenges was actually to reach low enough vacuum in our vacuum system. So it's 10 to the minus 8 or maybe even lower millibar to prevent any air damping. So adding these does not increase the damping, but if you would do it in air or at lower pressure, at higher pressures, then for sure you're right. Then they would actually decrease the Q factor. Did that answer your question or not?
Yeah, thank you so much. But it's still, I'm just a bit, I still have the question that, how they end up with high quality, even if you do them in the vacuum. How are they, positioned that string?
Yes. So one of the main damping mechanisms in these kind of strings is the fact that you create sound waves, and those sound waves, they travel to the side and they go into the substrate and you lose them. So you should prevent that from happening. So by creating these kind of structures, you create a kind of a mirror that reflects all the sound waves that travel here towards the substrate. You reflect them so that all the energy stays contained in the center of the string. And that requires the precise design of this structure, because any sound wave that goes into the substrate is lost, and you lose the energy. So this is like a bell that you ring, and it if you look, it continues ringing for more than 7 hours after exciting it. So you need to be very careful that the sound is not leaving your structure, because then you lose the energy.
Thank you so much, Peter.
We have other question from Hasret Ağırcan.
Okay. Is it in the chat? Yeah, I see.
Yes, chat.
For the curiosity for the strain experiment, did you analyze strain via Raman if there's ligand transition? When discussing higher tension leading to increased sound speed, could this be related to the ligand transition? So we did not use Raman. Raman can be used to measure strains. However, the resolution of Raman for strain is not as high as the resonance frequency. So we did not do it in this case. The strains that we are seeing, or the change in the strains, are probably too small to detect via Raman, although it depends a little bit on how good your Raman system is, of course. The increased sound speed during higher tension, there was no, that was purely effect of the mechanical properties. There was no strain-induced transitions occurring. Although, those can occur at high strains, but in this case, I don't think this was happening. The strains are too low to cause those transitions. But thanks for the question.
Thanks. Thank you, everybody.
Thank you for your presentation.
Okay.
And thank you all participants for your participation.
It was a pleasure. Thank you and goodbye.
Take care. Bye.
Thank you.
Evet, teşekkürler.